Okay, so we're going to continue talking about the cardiovascular system, and we were talking about blood vessels, and we were talking about the physical things that affect the flow of blood. And so you remember that I gave you this little formula where F is flow, and then we get the difference in pressure divided by R. And does anybody remember what R represents in this formula? Resistance to flow. And generally that has to do with the friction that is in the blood as it moves through the blood vessels. So what are some things that affect resistance and would increase resistance and therefore decrease flow? Friction, and so when you constrict the blood vessel, the blood is in more contact with the sides of the vessel, and so the constriction of the blood vessel, as we decrease the diameter, that is going to also decrease the flow. What else? Viscosity, and so what determines the viscosity of your blood? The thickness, but it's also the proportion of red blood cells. So if you have polycythemia, if you have too many red blood cells, then that is going to increase the viscosity of the blood. Also, if you are dehydrated, that is also going to affect the viscosity. So if you're like low water content in the blood would also increase it. Because remember, the hematocrit value is the proportion of the whole blood, which includes the blood plasma. So if that hematocrit value goes up, it would go up if the proportion of the plasma went down. Okay. And then we talked about the length of the blood vessels. And so there's going to be more resistance to flow as you go out to the furthest reaches of the blood vessels. So when we look at the blood vessels, if we look at the way that the blood flows, it starts in the large conducting arteries, right? And so arteries have a relatively high rate of blood flow because they have a relatively high pressure, because it's being forced right out of the heart, and there hasn't been a lot of time for resistance to decrease the flow. So arteries, then we go into smaller and smaller and smaller until we get to structures that are called arterioles. Oops, spelled that wrong. I could figure out how to erase. Somebody was trying to help me with that. I just go like white over it. Like white out. That'll work. Arterioles. Okay. So arterioles are very thin arteries. They're very small arteries. And then remember, from the arterioles, we go into capillaries. Okay. From the capillaries, we go into, the blood travels into venules. So notice that I left out the I. So for some reason, they removed the I from that word. So a venule is just a small vein. And then the veins come together into larger veins. So from the venules, we would go into larger and larger veins. Okay. So the flow of blood starts out relatively high because there is a high pressure, but as it goes into smaller and smaller blood vessels, the flow of blood drops off because resistance becomes very high. So resistance to blood flow is highest in the capillaries. So highest resistance to flow. So what that means is that when the veins carry the blood back, that means that it is under very low pressure as it carries it back. Okay, so we'll talk about the different pressures. So this is demonstrated graphically in your book so that you can see how blood pressure and blood flow, if we're just looking at pressure, how it drops off. So in the aorta, notice that there is a pulse, and this is due to the contraction of the ventricles. And so the pressure goes from 120 to 80, right? So that's your normal blood pressure. Your systolic pressure is when your ventricles are contracting, and your diastolic pressure is when your ventricles are relaxing. And then you notice that this graph actually becomes the steepest right here at the arterioles, right? So it kind of drops off, that blood pressure would drop off, and then blood flow would also drop off. So notice at the arterioles, it's about 60 millimeters of mercury, right? At the arteries, it's more like, if we looked at the mean, it's more like 90. And then if we look in the veins, coming back, the veins could have a really low blood pressure at like maybe even 10 or 15 millimeters of mercury. So you just see that how blood flow, due to the differences in blood pressure, drop off as the blood travels through the circulatory system. So today we're going to talk about blood pressure, and this is measured in millimeters of mercury. And that is actually the same units that our atmospheric pressure is measured at. So like you could say that our atmospheric pressure is 760 millimeters of mercury, right? So this is the amount of pressure exerted on a column, a given standard column of mercury, and then it gives the units of how tall that column would be. So this is millimeters of mercury. So when we're talking about our blood pressure, we're generally talking about arterial blood pressure. And it is in the brachial artery. Although now they are using the, artery. They are using the radial artery. So if you've been to the doctor recently, instead of putting the blood pressure cuff up here, they put it around your wrist, right? So they're using a different artery. And that's probably a good idea, because when you take blood pressure readings, you're actually cutting off the blood supply by collapsing the artery. So in the brachial artery, so I'll put radial artery would be at the wrist. So this is the wrist version. So what do you use? Yeah. Maybe that's more, I don't know, effective.
I just think technology is coming a really long way, but I haven't seen that yet. But I don't see that happening for a long time, being like a common thing, like in hospitals. And
so they put it around your wrist and they have you go like this.
Yeah.
Okay, but when you first do it in the emergency, okay. So that's the brachial artery. So when we look at that pressure, it generally can be over 120 over about 80 millimeters of mercury. So this is normal. So the high value, this is my systolic pressure. And this is my diastolic pressure. And so you remember that systole refers to contractions. And so this would actually be ventricular systole. So this is where the ventricle is contracting, and that is why that pressure is high. So this is the contraction of the ventricle. So we say that it is ventricular systole. And this is ventricular diastole. So that is when the ventricle is relaxing. So what they're listening for when you take blood pressure is the flow of blood through the brachial artery. So if we look at an image here that shows this, this is not from your book. This is just from the internet. So when you inflate the blood pressure cuff, you cut off the flow of blood. And so you notice that they use a stethoscope, and you put the stethoscope underneath the blood pressure cuff, because what you're looking for is where you start hearing a sound. And you'll see this on the little dial if you're using a manual blood pressure cuff reading, and it'll go boom, 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 boom. And so you'll actually see the pulse right in there. And it sounds like this. It sounds like a click, so it's like a, you can hear it. And then all of a sudden it will stop making sound. So when you first start hearing the sound, so when you actually do it, so you cut off blood flow in the artery. Okay. And then you listen for turbulent flow. So this actually makes a sound that you can hear. And then the third thing that you do is you listen for when the sounds stop. So listen for when sound stops. And that means that even when the ventricles are relaxed, the blood is flowing through and not making a sound. So it's actually got what they call a laminar or an even flow of blood through it. So you can see that that's what the two measurements measure. So when the blood is first able to break through, right, and flow through the vessel, you can hear a sound. And then when it can flow through the vessel without making a noise, that would be when you have diastolic pressure. So those are what they're measuring. So we can also talk about what is called pulse pressure. And this is what you actually feel at the major pulses or pulse points in the body. And the pulse pressure is the difference between systole and diastole. Yes, well, I'm going to talk to you what MAP is. Okay, so it's not quite the same thing. But you have to calculate the pulse pressure in order to get the mean arterial pressure. That's the difference between the systole and the diastole. So in this case, what would be the pulse pressure? 120 minus 80. So it would be 40 millimeters of mercury. So you can feel the pulse pressure at the pulse points. Okay, so this is where you can feel it. These are also called pressure points. So it's good to know where the pressure points are in case you have damage to a blood vessel and blood is being lost. You can put pressure on that given point, and that will help to slow the flow of blood into that body part so you can reduce the loss of blood. And so we often just think of the neck and the wrist and maybe the elbow as being examples of pressure points. But there's also places, right? So the radial artery, the femoral artery would be in the groin area. The popliteal artery is behind the back of the knee. And then you have the tibial artery, posterior one, and then the artery that serves the feet. And so these are places where you can feel the pulse, but there's also places where you could apply pressure to prevent blood loss. So notice these are all arteries. You would not feel a pulse in a vein because the veins do not have a difference in pressure. The pressure stays constant. Okay, so then we can talk about what MAP is. And MAP is just the mean arterial pressure. So this is important because this is what delivers oxygen and nutrients to the tissues. And so this is what determines if the blood is going to flow into the tissues. And so we can calculate MAP as being the diastolic pressure. So MAP equals the diastolic pressure plus the pulse pressure divided by 3. Okay. So what was our diastolic pressure in the previous example? 80. And the pulse pressure was 40. And then you divide 40 by 3, and then this equals 99. Is that right? 99.
Why 3?
I'm not sure why 3. I actually didn't try to figure out how they derived this, but this is the calculation. Okay, so that's your mean arterial pressure. So is that 1940 divided by 3? No, that's not right. Is it 96? Sorry. 40 goes into 3. 1, 3, 10 goes into 3, 9. Okay, so it'd be 93. Sorry.
Can you go 80 plus 40 divided by 3?
No, you have to do the 40 divided by 3.
I was so confused the whole time when we were getting 90 from. I was adding 80 plus 40 and then dividing by 3.
Oh, no.
So that's a good, I'm glad you
Yeah.
asked. I was so confused.
No, I think it says you have to divide first. Yeah, so that's 93. Okay. Okay, so now if we compare this to the venous blood pressure, remember that there is no systolic or diastolic pressure in terms of venous, right? So the pressure is constant. The pressure is low. So you could say maybe 15 millimeters of mercury. And so remember that that's why sometimes it's very difficult to get the blood to return back to the heart from the lower extremities. Specifically, if you're standing in one place for very long, you can get the pooling of blood in the feet, and that can cause problems, specifically if clotting happens. And it can also cause damage to the veins. And so the pooling of blood can lead to what is referred to as varicose veins. Okay, so varicose veins are damaged veins that bulge outward. And so I think maybe varicose veins, like just being able to see the veins on our legs is pretty normal, specifically as you age. But if you look at varicose veins and you look at some images of them, you'll notice that they can become extreme, right? So the people's legs start to look really ropey. And you can see that the blood is just pooling in that area. And that could be really dangerous because what that means is that the valves are damaged, right? So we have damaged valves, and the blood flows in the wrong direction. Right, and clotting is more likely.
Not painful. Like, not like painful, but.
I would imagine the pooling of the blood in your feet sometimes makes it feel bad, you know. So what they can do is that they do a procedure which is called stripping the veins, which is kind of just like it sounds. So they just poke a hole and they into the skin, and then they find the vein and they just strip it out. So they just pull it out and they actually remove it. And that is better to get these veins out than to leave them in, specifically due to the clotting. But then you have a problem of getting that extra blood back up. So you might, after you strip your veins, we talked about those compression stockings, and that would help to move the blood back up towards the heart. Okay, so the movement of blood is due to a couple of things in the veins. One is what is referred to as the muscular pump. So veins are associated with skeletal muscle. So movement helps to pump the blood. So getting up and walking around and not having to stand in one place all day for work, for example. So that would be one. And then we also have what is called the respiratory pump, which is kind of interesting because it has to do with the changes in the pressures of the abdominal cavity and the thoracic cavity. So when you take an inhalation, your diaphragm actually moves down into the abdominal region, and that actually causes a increase in pressure in the abdominal cavity. So blood vessels that are coming up through the abdominal cavity are kind of squeezed, right? So during inhalation, so that is taking breath into the lungs, the abdominal pressure increases. And squeezes the blood vessels. And at the same time, the thoracic region, actually in the chest where the lungs are, that thoracic actually decreases the pressure, and so it allows the blood to more easily flow up into the thoracic body cavity because the thoracic body cavity has a decrease in pressure. So decreased pressure in the thoracic region helps move the blood. Okay, so breathing helps to pump the blood in the veins. And then we also have some ability with the sympathetic nervous system. So remember that that's the fight or flight. The sympathetic division of the nervous system is actually the only part that innervates the blood vessels. So the parasympathetic division does not innervate the blood vessels. So sympathetic vasoconstriction of veins. So remember vasoconstriction, you decrease the diameter and then that builds pressure and it helps to get the blood to move up. Okay? And then also remember that we have valves. Right? And so that helps to prevent backflow. Okay. Let's see. So in this diagram, they're showing the muscular pumping action. The contracted skeletal muscles actually force the blood up. The valves keep the blood from flowing in the wrong direction. Okay. So the next thing that we're going to talk about is the regulation of blood pressure. So BP is just blood pressure. And so when we're talking about regulation of blood pressure, we can go back to the difference in pressure. So that's my delta P. So delta just means difference. And so remember that in order for blood to flow, it has to go from a high pressure to a low pressure. If delta P goes to 0, then flow will stop. So remember that last equation we talked about. So delta P is actually equal to CO, which stands for what? Cardiac output, right? Plus resistance. Okay. So in order to regulate my blood pressure, I can do two things. I could, neurologically. So one thing that I could do is I could increase my cardiac output. Because if I increase my cardiac output, I'm going to increase my blood pressure. And then I should want to decrease my resistance. So this is actually not plus, sorry. This is a times. I'm liking that white out. So this is times, okay? So I can also influence blood pressure by changing the resistance. And one thing that directly affects resistance is the diameter of the blood vessel. So if we look at a diagram from your book, right? So notice cardiac output. If we increase the amount of blood that is being pumped out, which is stroke volume of the left ventricle, that is going to increase the pressure. If I increase heart rate, that is also going to increase the pressure, okay? So here I could say cardiac output is equal to stroke volume plus heart rate. So that SV is stroke volume. You might want to write that out. So if I increase my heart rate, I'm going to increase my blood pressure. If I increase the contraction of the ventricle and make it more forceful, I'm going to increase my stroke volume, and that's going to also increase my cardiac output. Okay. So for resistance, remember that resistance could be due to, so I'll just put due to with a little semicolon, due to a decrease in blood vessel diameter. So a decrease in blood vessel diameter is going to increase resistance, and it's going to increase the difference in pressure. Probably more unlikely would be changing your blood viscosity or your blood vessel length quickly in order to maintain blood pressure regulation. So we'll just pay attention to the diameter. Okay. Okay. So let's look at the neural mechanism, neural regulation. So when we talk about neural regulation, we talk about receptors. So receptors are just modified neurons that can detect stimuli. So there's two important types of receptors for the neural regulation of blood pressure. One is the baroreceptors. So where have you heard baro before? That's an R, B-A-R-O. In terms of pressure, what do we measure atmospheric pressure with? A barometer, right? So barometers are measuring blood pressure. So this is pressure exerted on the wall of a vessel. And we have baroreceptors in what are called our carotid sinuses. So these are near the carotid arteries, which we'll talk about, which deliver blood to the brain. We also have chemoreceptors. And so these detect chemicals, and specifically, we're going to say that these detect pH in this example. So these are located in the near the aorta. Okay, so that's another blood vessel that's leaving the heart. And this relates to the presence of carbon dioxide in the blood. So as carbon dioxide in the blood increases, so let's say you're exercising and you're producing more CO2, and that is in the blood. So the CO2 gets dissolved in the blood, and the CO2 produces, when it combines with water, when carbon dioxide combines with water, it produces a weak acid which is called carbonic acid. Okay, so carbonic acid is then going to release hydrogen ions into solution. So hydrogen ions are going to be released, plus you don't need to know the name of these, but it's just the carbon dioxide mixing with water that causes the hydrogen ions to be released. And if you have a lot of hydrogen ions, is it low pH or high pH? Low, right? So this would be a decrease in pH. Okay, so these chemoreceptors can affect the blood pressure. We also need in our regulation, we need a control center. And for our blood vessels and our heart, this is the medulla oblongata. So this is in the brain stem. This is the cardiovascular center. We'll call them centers. So these are the neurons that regulate that. And then the control center is going to send a signal out to what we call the effectors. And in this case, the effectors are going to be the heart, right? So we can either increase heart rate or decrease heart rate, depending upon what is needed. And when we increase heart rate, what happens to blood pressure? It also increases, right? Okay. Also, this goes out to the blood vessels, specifically the arteries, right? So this can cause vasoconstriction or vasodilation. Okay. So let's say the pH in the blood has dropped. What is going to happen to heart rate? If the pH of the blood drops and the chemoreceptors detect that, what is the medulla, how's the medulla oblongata going to respond? Increase heart rate, right? So if you have a low pH, you increase the heart rate, and that's going to boost blood pressure. So in your exercise, you would predict that your blood pressure is going to go up, okay? The opposite, if your blood pH got too high and was too basic and not acidic enough, then you'd have a decrease in heart rate. And what that's going to do is that is going to help you to retain carbon dioxide in the blood so that your blood pH will go back down. You could also, if you needed more oxygen, so if your blood pressure was low and you, like say for example, if the blood pressure to your brain was too low to supply the blood necessary, the oxygen and nutrients necessary to the brain, then you're going to have vasoconstriction, and that is going to boost the blood pressure and send more oxygen-rich blood to the brain. Okay. So in your book, you would want to take a look at the diagrams. Okay. So these are the two effectors. This is the receptor. This, the brain, would be the control center. So if my blood pressure is too high, it's going to cause a decrease in heart rate, and it's going to cause a vasodilation. So let's write that down. So if blood pressure is too high, and what is that called when your blood pressure is too high? We'll talk about it. It's called hypertension, right? So blood pressure too high. Okay. Heart rate decreases. Vasodilation happens. Blood pressure too low, the opposite. You'll get an increase in heart rate, and you'll get vasoconstriction of the blood vessels. Oops, yes, vasoconstriction. So in the next diagram, they show it being too low, right? So the stimulus here is the blood pressure is too low. The baroreceptor can detect that. The control center sends out a signal. And the sympathetic nervous system is going to innervate the SA node and cause heart rate to increase. It's going to innervate the smooth muscle of the blood vessels and cause the smooth muscle to contract. So we cause vasoconstriction, and then that is going to cause us to go back to a normal range of blood pressure. Okay. So we also have a mechanism for regulating blood pressure through hormones. And so one of these is norepinephrine. Which is also called adrenaline. Epinephrine does the same thing, but we'll just talk about norepinephrine. We're going to talk about norepinephrine and epinephrine when we talk at next quarter, when we talk about the endocrine glands. Okay, so this is adrenaline. So this is actually going to cause, when you have adrenaline, it's going to cause the blood vessels to contract. So this is vasoconstriction. What does adrenaline do to your heart rate? Cause it to go up. Okay, so that's one way that your endocrine system, your hormones, can regulate your blood pressure. Okay, the second one has to do with what is called angiotensin II. So just looking at that word, do you think it's going to cause vasoconstriction or vasodilation? Tensin, what does tensin mean? Contract, right? You're getting tense, you're contracting your muscles, right? So just looking at that, that means that it's going to cause contraction. So this causes vasoconstriction. This increases blood pressure. Right? Whenever you get constriction, that's going to increase resistance and that's going to increase pressure. Okay. The third one that can cause it is called antidiuretic hormone. This is ADH. So what is diuresis? Anybody know? When you're on a diuretic drug, or if you take a diuretic, what does it cause in your body? Liquid. So it's actually your urine. So diuresis is actually urine production, right? So what this does, antidiuretic hormone causes a decrease in the loss of water in your urine so that you reabsorb more water. So this causes an increase in the reabsorption of water in the kidneys. So this is important if you become if you stop drinking water, right? And you're starting to get dehydrated, your body should start to really focus on producing very concentrated urine, which is why your urine becomes more yellow and darker colored the more dehydrated you get. And so what this is going to do is this is going to increase blood volume. So how is that going to affect blood pressure? Is that going to cause a decrease in blood pressure or an increase in blood pressure. If you have more water, so say if you have water through your hose, you turn the water on a little bit, or you turn the water on a lot. That's going to increase pressure, right? If I have a lot more blood, my blood volume increases. This is actually going to increase blood pressure. Okay. And so the ADH hormone has another name that they call I had it in my mind, pressin. Let's see. Yeah, vasopressin. I don't think I'm saying that right, but so pressing on the blood vessels. Okay, so it's a vasopressin. So if you take diuretic drugs, and some of these things that are actually diuretics could be something that we ingest. So what is something that causes you to urinate more and to produce more volume of urine? Well, drinking water does, but it's not, I guess water is a diuretic. Yeah, so what is it that you take, that you like eat, that makes you pee more? Asparagus, well, it makes your pee stinky. Okay, caffeine, alcohol, right? Vitamin C. So if you take a lot of vitamin C, in order to get rid of it, it has to be diluted in the urine, right? So you actually produce more urine. So diuretics are actually if you're put on a diuretic, would you expect your blood pressure to go up or to go down? Down, right? So this decreases blood pressure. So if you have chronically high blood pressure, you might be put on diuretics to decrease your blood pressure. Okay. So it's kind of interesting when you drink coffee or alcohol, it can cause you to become dehydrated because you're not just urinating out the caffeine or the alcohol, but it is actually making you produce more dilute urine. And so they can cause dehydration over time. Okay, then there is one that's really interesting to me, at least, because it's produced by the atria of the heart. So when we think about hormones, we think about glands. We don't really think of the atria of the heart as a gland, but it is called the ANP, which stands for atrial. Oh, now my pen's not working. Atrial natriuretic. I need to make sure I can spell it. And these are two words, sorry. There's a space there. Dipeptide. So you could just abbreviate this as ANP. No, there's three words. So atrial, and then there's a space, natriuretic dipeptide. And this is a hormone produced by the right atria. And it is actually produced in response to high blood pressure. So if there's high blood pressure, ANP is released. And this causes vasodilation. So all the other ones that we talked about, like norepinephrine and angiotensin, those were actually constrictors. This is a vasodilator. So this was going to actually decrease your blood pressure. So this is the stimulus, and this is the response. Okay, so those were rather short-term mechanisms for blood pressure. Like if I'm going to exercise, I need to boost my blood pressure, right? If my adrenaline gets released, it's going to boost the blood pressure during fight or flight. But we also have long-term regulation of blood pressure. And so what is renal? What does renal mean? What is renal? Kidney. And so you ask, why do kidneys have anything to do with the regulation of blood pressure? The answer is that the kidneys have to filter the blood. And the blood has to come in at a high enough pressure to produce the filtrate. So the blood comes into the capillaries of the kidney and it has to produce be just at the right blood pressure to produce the filtrate. It can't be too high or you're going to get kidney damage. And it can't be too low or you're going to not filter the blood, right? So too high, the blood pressure is too high, right? It can damage kidneys. So hypertension can actually lead to kidney failure. And you can tell if your kidneys have been damaged because there's blood in the urine. So normally there should be no red blood cells in the urine. So if you're bleeding, if you're urinating and it looks like there's blood in your urine, you know there's something wrong with your kidneys, okay? If the blood pressure is too low, the kidneys cannot filter the blood. So this is why the kidneys are probably important in being involved in the regulation of blood pressure. So there are actually sensors in the blood vessels that are leading up to the kidney that can detect blood pressure. So kidney cells detect blood pressure. So that these would be receptors, right? So they're not in the brain, they're not in the blood vessels, they're actually in the kidneys. So the kidney responds directly by then releasing a hormone, and the hormone that they release is called renin. So will release renin if blood pressure is too low. So what renin does is it is actually an enzyme. And so renin is involved in converting angiotensinogen to angiotensin. So this is renin. So the renin is an enzyme. Angiotensinogen is the inactive chemical that is in your blood. It is inactive. So anytime you see inogen, that generally means that it is the inactive form of something. The angiotensin is in the blood and it is active. Right? And the angiotensin causes what? Vasoconstriction. So that is going to boost blood pressure so that the blood will come in at a higher rate so that the blood can be filtered of all the toxins like the urea that is in the blood that needs to be filtered out. Okay. Okay. The other thing that it does, so this is like one, will release renin. The second thing is that it does is it stimulates the adrenal glands to release aldosterone. So this is a steroid hormone. So just think sterone, right? It is actually a hormone that is going to affect the kidney. So what it does is it causes the kidney to increase reabsorption of sodium. When you increase the reabsorption of sodium, that is also going to cause the increase in the reabsorption of water. So I'll put thus, more water is reabsorbed, more water is reabsorbed. And what does that do to blood volume? Increases blood volume. What does that do to blood pressure? Increases blood pressure. Okay, so if we look at a diagram in your book that summarizes this information, and this is actually one of your essay questions that you need to be responsible for. So I gave out, did everybody get the copy of the review sheet? So this is a good example of, or diagram that kind of summarizes this idea. So we have a decrease in arterial pressure. The kidney releases renin. It then ultimately catalyzes a chemical reaction that produces the angiotensin, which then causes the aldosterone to be secreted, which then causes an increase in sodium reabsorption. And these both cause the blood volume and vasoconstriction to happen. So that increases your arterial pressure. And so this is what is referred to as the renin angiotensinogen aldosterone mechanism, okay, of maintaining blood pressure. Okay, so the last thing we're going to talk about is hypertension and hypotension. So think hyper means high, tension means the blood vessels are too much pressure, right? There's too much pressure on your blood vessels. So this is high blood pressure. And it has to be sustained. So you can have blood pressure going over this, but if it is sustained at higher, this or higher, this is kind of the cutoff. So that's 140 over 90. So it's really annoying with what the doctor will give you if they think you have high blood pressure. They'll give you this little pack thing you have to put in your pocket or your purse, right? You have to carry it around. You just have to keep checking your blood pressure and noting what it is. So they have to collect a lot of data over different times to determine whether or not you truly have hypertension, or do you just get upset when you go to the doctor's office, right? And it causes your blood pressure to be high. And so you have to log data for it to be diagnosed as being hypertension. So some things that can happen with hypertension is, this is sometimes referred to as the silent killer, because it can have no symptoms for like 10 or 20 years. So a person could be hypertensive and they don't even know it. And then all of a sudden, you have all these problems that just happen, right? So 10 to 20 years, no symptoms, right? And then you start getting symptoms. And so what it does, what hypertension does, is it strains the heart. And one reason that it does this is if your blood pressure is high in your vessels, the heart is going to have to contract more forcefully to get blood against that pressure, right? And so your heart is going to become weak. Okay, so it weakens the heart. So it can actually, So it can actually lead to congestive heart failure. It also puts strains on the blood vessels. Right, so you could actually have, from this, you could have a blood vessel rupturing and causing blood to move out into the tissues. And if this is in the brain, this is called a cerebral aneurysm. So this is a ruptured blood vessel in the brain. And this causes or leads to a stroke where some of the tissue, some of the nervous tissue in the brain will die, right? And then generally that affects one side of your body. So sometimes they call this a brain attack, right? So people say that you should know the symptoms of a brain attack like you know the symptoms of a heart attack. So what are some symptoms of a person having a stroke? Does anybody know? Slurred speech. What else? One side of their body, maybe one side of their face starting to droop. What else? Speech. And then what about their eyes? Yeah, and they also start to have blurred vision. So one of the things is you can have like a minor stroke. So somebody could have be at a party and all of a sudden they're like, oh, I feel really weird, and they're having some of those symptoms, and then they go home and go to bed, and then they have a major stroke in the middle of the night. So if you knew right when that minor stroke occurred and you went to the hospital to deal with it and to lower the blood pressure, the major stroke that killed the person probably wouldn't happen, right? So that is important to know. Okay, so this can cause also damage to the kidneys and other vascular disease. So it can also lead to, we'll put strains the kidneys. So it can lead to renal failure. So causes. Diet. What specifically in your diet can cause you to be hypertensive? Salt, right? We'll talk about cholesterol when we talk about atherosclerosis, but there's some controversy over whether diets high in fat and cholesterol can also cause this because of blockages of blood vessels. But salt is the big one because we kind of have over-salted our food. So specifically processed food tends to be way over-salted. And so it's really interesting because your taste for salt will adjust to how you take it in. So for example, if you stop eating a lot of processed foods and then you eat something that's processed, you're like, whoa, this is way saltier than I remember it, right? Kind of like the idea with sweetness too, are the thresholds of like what we think are normal versus extreme adjust if we decrease the salt, right? So grandma and grandpa, they're always like, oh, we don't use salt anymore, right? And you're like, oh, this is so bland. Okay. It's because your taste buds have not adjusted. Okay. Diabetes, mellitus, obesity, stress is one, and a big one is smoking. And the reason for that is that nicotine is actually a vasoconstrictor. So smoking can cause the constriction of your blood vessels. Yeah, but it actually kind of, it's nicotine I don't understand because it actually kind of gives you energy too. Yeah, so it actually speeds up your heart rate. So I don't know why people say it relaxes them because it actually doesn't. Yeah, okay. Okay, so the last thing we'll talk about is the opposite of hypertension. Oops, sorry, we'll talk about that next, which is hypotension. Generally, hypotension is not near the problem. It is the break-off, the cutoff is 90/60. And the thing about hypotension is that sometimes people can pass out because they have low blood pressure. So if the blood pressure is not able to get up past gravity to come up to the brain, it can cause fainting, right? So it causes fainting. And specifically, if you get up too fast, right? So if you go from lying down to standing, you probably have all experienced this. This is actually hypotension caused from postural change. So if I'm lying down and all of a sudden I jump up and I'm like, whoa, and like my vision goes all white, I can't see anything, and I almost fall down, that is because of hypotension. So your blood, your body, your heart rate didn't have time to respond, and your blood vessels didn't have time to respond to standing up. And so sometimes older people have a problem with that. You know, they have to get up really slow, right? And so what is it? What is the blood pressure that is the difference between your blood pressure lying down and standing? Does anybody know what that's called? Does anybody measure that?
Oh, like orthostatic.
Yes. Okay. So the difference between these is called orthostatic blood pressure. All right, so I'm lying down to standing up. And if that gets too low, then it can cause problems.
They like changed it, like at the hospital, now we do it like standing for 1 minute and they stand for 2 more and then you take it. So 1 minute to 3.
Huh. Okay, any questions? I think we'll stop there for today. So you have a quiz on Monday next week. We do have lab, and what we're going to be doing is blood vessels. Oh, and I wanted to mention, if you go into the library and you go up the stairs to the mezzanine, like where the English people now have their offices, there's actually an A&P room where we have some models. And so the heart model is in that A&P room. So if you wanted to go review that heart model, you can go into that room. And then also the circulatory vessel model is in that room as well. So that's where you would be able to find those models so that you can study for the lab practical.